I'll just give you a brief overview of where we're going to head in this talk. I'm going to start by talking about landfill licence conditions and how they relate to hotspots and fires in landfills, and from that then go on to define hotspots, talk about various hotspot indicators, then go on to the current use of drones in landfills and why drone thermal mapping as opposed to other methods that are currently being used. I'll talk about the general process and deliverables and the limitations of using drone for thermal mapping, and just some other potential uses for drone thermal mapping in landfills. I want to start with two questions, and if you're here this afternoon and you are responsible for the day-to-day running of a landfill, the two questions: do you know if your current licence says anything about hotspots or fires? Conversations I've had with people, they generally don't know that it's a specific condition in their licence, and a couple of examples here of different licence condition wording. You got there, a licensee must have in place and implement procedures to minimise the risk of fires at the premises, and more specifically, another licence condition, you must take measures to prevent hotspots and to ensure that appropriate management procedures are in place and implemented to prevent, identify and cool hotspots within the waste mass. So it's going to be a bit different from state to state, requirements-wise, but generally those two licence requirements are in there. And the second question is, what's your current approach to identifying hotspots, or better still, do you even have an approach in finding hotspots at the moment? Now, there's been many prominent incidents just recently in the news over the last couple of years. I'll just go through a few of them now, just it might refresh your memory. In late 2018, there was a fire at a landfill in Anglesey in Victoria. It was a subsurface fire in a capped part of the landfill, and this part had been capped for 18 months. So it was no longer being used for 18 months and fully capped. The extent of the fire was 4 metres below the surface, and it required 6 fire crews to get the fire under control as it went to the surface. And the fire crews had their own thermal camera to try and find the extent of the fire, and getting readings close to 100 degrees Celsius on the surface as a result of these fires, and they're able to map out the extent of it. The EPA issued the local council there a fine for over $8,000 for breach of their licence, and that's in addition to the other costs like emergency services costs, clean-up costs, downtime costs as well. And the report that the EPA gave specifically mentions that landfills have a responsibility to have a comprehensive hotspot monitoring program. And it's interesting that this site in Anglesey actually did use thermal cameras on their site, but they had one thermal camera attached to a pole at the current tipping face, and that was the extent of their thermal imagery, and the ruling from the EPA said that's not enough, it has to go to cap cells as well. Just recently, a couple of months ago, there was the Corangan Island waste fire near Newcastle, and this was an underground fire in close proximity to toxic waste storage, and in that case there was 10 separate fire spots, all started by a grass fire that went over an old cap area, and the clean-up action's still underway at the moment, and they're not 100% sure of how to actually put out some of those fires, and running some experiments at the moment. And there was a big one down in Melbourne in July 2017 at a waste recycling plant, and that burned for 11 days, and it caused a significant public nuisance and a loss of reputation in the community, where people weren't allowed in their homes for days on end because of this. The EPA undertook a forced closure of the site, and as a result, all the stockpiled recyclables from almost half of the councils in Victoria used this site. They were then sent to landfill as a result. So there's a lot of lost opportunity there. And to make it worse for the operator, a class action was started against them. So there's numerous examples the last couple of years. You can Google EPA news, landfill fires, you'll get a lot of things come up, but that's just a snippet of what you can expect in landfill fires. So what is a hotspot? The basic definition, an area of elevated temperature within a landfill indicating some sort of subsurface smouldering or spontaneous combustion. And it can fall into two categories. It can either be a shallow hotspot, and that's from the surface down to 5 metres, or it can be a deep one, so 5 metres and below that. Of course, shallow hotspots and immediately subsurface fires are the easiest ones to remedy. It's just a simple case of taking off a couple of lifts of waste and fixing it up. But it's the deep-seated ones that take a significant amount of excavation to get down to try and remedy. Many here would be familiar with the concept of the fire triangle. That's where a fire needs three things to be a fire, and take away one of those things, a fire ceases to be, or you can stop a fire occurring. And essentially fires, a chemical reaction involving heat, involving fuel and some sort of supporter, in most cases oxygen. And all three of these must exist simultaneously together for a fire to occur. And that's the same in landfill situations. You've got, in landfills, subsurface, you've got heat from decomposition or chemical reaction. And interestingly, over the last couple of years, we're seeing an increase in heating coming from lithium battery corrosion and lithium battery breakdown. You've got fuel from combustible waste or flammable gas. But the key trigger for a landfill subsurface fire will be oxygen, and that comes from ingress into the gas extraction system or through some sort of line of failure. You can't get away from the heat and the fuel in a landfill, but you can and do a lot to get rid of the oxygen, and that's a result of the capping layers, gas extraction, all those sort of things, really to limit that oxygen in the landfill mass. Hotspots, especially deep hotspots, most often start through spontaneous combustion. And that's where a buried heat source in the waste mass, it continues to rise in temperature faster than the heat can dissipate out. And if heat increases beyond the immediate surrounding material's ignition point, and if there's sufficient oxygen in that area, then self-ignition occurs and we have a subsurface fire or a hotspot. Talking about hotspot indicators, there's quite a few of them. The most obvious one, of course, is rising smoke or steam. You've also got increased cap surface temperatures, surface temperatures above 70 degrees Celsius. You've got areas of increased smouldering odours. You've got unusual or rapid cap settlement, and this is caused by subsurface cave-ins as a result of fires below. You've got elevated carbon monoxide levels, somewhere in the region greater than 1,000 parts per million. Increased gas extraction temperatures above 60 degrees Celsius, increased leachate temperatures above 40 degrees, hot to touch leachate or gas wells, soot in the extraction wells or risers, and localised stressed or dead cap vegetation. They're all pointers. Take one in and by itself might not necessarily point to a subsurface fire, but if you get a few of those indicators occurring simultaneously, that would be a good reason to think something's going on below the surface. Many landfills now, they're starting to use drones in day-to-day operations, and our company, we do a lot of drone work. We do it in combination with normal aeroplane flyovers, day-to-day ground surveys. So they all have a place in a landfill, day-to-day landfill work, but drones, though they're not as accurate as a ground survey and they're not as accurate as stereo mapping from large-scale aerial flyovers, if you're happy with accuracies of 50 mil to 100 mil, then they're a really good tool to cover a lot of ground quite quickly and get you, current uses you can see up there, monthly self flyovers, airspace, cut fill plans, medium scale ortho images and site inspections. You've got stockpiles, cell construction imagery. A few councils have been doing that just as a compliance with their outsourced cell building, cell construction. Medium scale topographic mapping and differential site models where the changes in a particular area, whether through filling or excavation, are monitored date to date in that. So why drone thermal mapping? First of all, what is a thermal image? Now, everything has some form of infrared radiation, and that increases as temperature increases. And a thermal image is something that captures that thermal energy and presents it in some sort of reflectance way. It's judged by reflectance values. It presents it in some sort of way that are visible in our visible spectrum, that we can understand what's going on through that infrared, what's happening in the infrared wavelength. Now, the traditional approach is a site walkover with a handheld imager, but there's a couple of challenges with this. The first challenge is it's limited to where you walk. So no one's going to walk a 1 metre grid over a closed cell, let alone a 10 metre grid. You might get a 20 metre grid, but even still that's going to take a little while depending on the cell size. So that's the first challenge for handheld. The second challenge is you're limited with a handheld camera, particularly in the direction that you're taking the image. So if you're taking an image, you have the tendency to become parallel to the heat source, the ground that you're measuring, instead of perpendicular to the heat source and measuring it that way. So it's a bit of a challenge with the handheld imaging approach. And drone technology can meet this, and it easily allows whole cap and site thermal mapping. It's not limited to a nominal gridded walkover of a site, but it's also perpendicular, viewing straight down to the image being measured, so you get a better idea of spread of any potential hotspots. And it's also quick and economical. A standard cell, it's half an hour to map it out. There's a lot more in the office side of things, interpretation of the data, but it's quite quick out on site. It's a good initial screening tool at highlighting areas for further investigation, and initial's the key here. It's a good initial tool, and then from that you would then have probably close-up imagery. You might take some carbon monoxide levels, which are a really good indicator of fires, and you might put down some temperature probes in that area. But this thermal mapping, broad acre thermal mapping as a start is a good screening tool. And the benefits of whole site mapping is that hotspots are spatially located to the site's coordinate system and comparable flyover to flyover, so you get to see how things are growing, whether you do them quarterly to quarterly, monthly to monthly, whatever the time frame is. The general process, the first step is flight planning and regulatory steps. So CASA are quite strict on who can operate drones, and you have to go through a lot of red tape to be able to get pilot's licence, operator certificates, and they require the use of checklists to see if you can fly there, what you need to do to fly there. So that's the first step, and then planning how high you're going to fly, what sort of overlap you want, what sort of ground sampling distance, the flight path and things like that. When we fly, we tend to fly separate thermal and normal colour imagery, and the reason we do that, it allows for any isolated hotspots in the thermal imagery, because they're on the same coordinate system, then to be overlaid on the aerial imagery, which is taken exactly the same time. So you be able to easily see how, sometimes it's not easy to look at a thermal image and see what's what, but if you digitise the extent of that thermal image, put it on the aerial, you can easily go there and see what's going on. You then process the thermal images, and you're talking about, for a normal cap, around 200 images per normal cell, and these all get stitched together based on reflectance values, and the end result is a whole site thermal ortho image, and if you're taking the normal colour imagery, a whole site colour image. From there, the hotspot identification occurs based on threshold levels, and this is used image editors and GIS packages to do that. And then finally, you give the client the data. That's either a site thermal image in JPEG or TIFF, or you've got PDF plans showing the hotspots, or you can even create a 3D thermal mesh that can be looked at in an online viewer. It's good technology, very, very useful data outputs, and the benefits far outweigh the limitations, but there are limitations you need to be aware of in using drones for thermal mapping. And currently, the limitations, thermal mapping is limited to approximately 30 hectares per mission. And the reason this is, thermal flyovers have to move a lot slower through the air to account for refresh rates in the camera. So normal drone flying speeds for a normal drone flyover would be 30 to 35 kilometres an hour, but you really have to drop that down to about 15 kilometres an hour for a thermal flyover, just so the camera has time to refresh and you're actually getting useful measurements on the ground there. Because we're going slower, it eats into battery time a lot more. So I suppose if you had endless supply of money, you could buy more batteries, but they're costly, and the balance, about 30 hectares is the limit at the moment. It's only suitable for identifying shallow hotspots, so that's 5 metres from the surface. However, shallow hotspots can be a good indication of deeper ones, but thermal images are only measuring the surface level, and from there you're making interpretive decisions based on those ground-based readings. It's a complementary technology and not a replacement technology. It's not a one-stop shop for everything. You still need to monitor gas and leachate temperatures. You still need to monitor oxygen levels, cap settlement, all things like that. This is really an initial screening tool to be used. And the other limitation, it can only be used when specific weather conditions are met. So you can't do it after recent rain because the rain's going to dampen, the ground temperatures. And it's best to do it early morning as well. So it's that way you don't have solar radiation heating up the grounds. And early on, when we were doing a couple of guinea pig runs on some sites, we were amazed at the data we could pick up until we created a 3D mesh and realised that on this hot day of 31 degrees, all the north sides of bund walls were all, really high temperatures. We were amazed, this technology is amazing, but when you looked into it, you worked out, that's solar radiation, it's not a hotspot. So we worked out that early on with that mistake. By far the most common question I get is, can I use thermal energy to find fugitive gas emissions like methane? And the short answer is it's possible, but not probable. A lot of things need to go right to find a fugitive gas emission using thermal. The leak has to be very high pressure to start off with. You can't have a methane leak where it dissipates through the atmosphere. It needs to be heated quite well. It needs to pressurise. The studies have shown that it needs to occur on days of low barometric pressure. And if it's not occurring on those days, then lots of inadequate readings are coming in regards just using thermal for gas detection. There are specific drones you can use for gas detection. It's a new technology, but it's quite under-tested at the moment, and you're looking at $150,000 just for the instrument. So it's not really worth it at the moment. But other uses that thermal images are good for: gas infrastructure monitoring. So you're talking about above ground leachate lines, gas wells, gas plants. You can see the example in the images there. You've got in the top right the initial reflectance image. This is a gas plant, and then you apply different filters to get down to meaningful data, and you can take temperature readings from that. We saw earlier a solar panel farm. That's a good way to use thermal. Solar farms are becoming a bit more commonplace on long-term closed landfill cells. And you can fly over a solar farm and easily identify which cells, which panels are not working. And organic stockpile monitoring, so compost and timber stockpiles that have a heightened risk of combustion with lower ignition points, they're useful for that as well. Some practical advice. Work out, to start off, what sort of aerial monitoring program would suit you. And this is an example of a couple of our landfill clients. They have biannual piloted flyovers, so aeroplane flyovers. That gives you whole site imagery, mapping and volumes for reporting, and also volume reconciliations. But at the same time, you can take simultaneously near-infrared imagery, and that gives an indication of cap stress through the vegetation dying off. You can see up in the top corner there's parts of that area where the vegetation's dying off, as shown in the near-infrared. Then clients will also use quarterly drone thermal flyovers as cap cells, comparing month to month, quarter to quarter, and monitor any unusual cap settlement between surveys, and monthly, quarterly drone flyers of active cells, and place waste for volumes and cut and fill plans. Another question would be good to ask is, do you need a complementary ground-based monitoring survey? So you can do a gridded methane or carbon monoxide survey, or after the thermal one's been done, isolating hotspots and going to take readings there as an indicator, further proof that something is going on below the surface there. So in conclusion, drone thermal imagery, it's a useful initial screening tool for hotspot identification. It has its limitations like all technology, and it's about managing the limitations to get you the best data for the job, and the benefits do far outweigh any limitations. The key question that I leave with you is check your licence. What does it say about hotspots? And do you have a hotspot monitoring program? Think long and hard about it, because at the end of the day, what's the cost of not taking some sort of preventive measures? You've got emergency costs, downtime costs, cap excavation and rehabilitation costs, licence breach. As a minimum, the EPA will give you an $8,000 fine for a licence breach. Environmental costs, and we're not talking about just atmospheric pollution, we're talking about fire water runoff. And there was a case for a landfill in Melbourne where the runoff affected 4 or 5 kilometres downstream, and they got into a lot of trouble for that. Reputation costs, that's a big one. Most landfills operate on a knife edge regarding some sort of local resident action group, and they're looking for any excuse to make trouble. And litigation costs, that'll be a big one. It's a multi-million dollar what if. You can get some further reading. There's some really good articles in there and be able to download the slides for that. Any questions?